brought to you by the North Carolina Office of Environmental Education and us at the North Carolina Museum of Natural Sciences. Thanks for being here. I'm your host. My name is Chris Smith. I'm an educator at the Museum of Natural Sciences, and I'm here with you every Wednesday at noon, where we meet interesting people making interesting discoveries and doing interesting things in the world of science, technology, engineering, mathematics, education, art, and more. Every Wednesday at noon, we gather right here at the museum's Facebook and YouTube channels in order to talk science, talk nature, talk environment, and really get a sense of what's going on out there in the world of science and nature and how it applies to our daily lives and our work. So glad that you could all be here tuned in. I'm sure we've got a great program for you today. We've got a great speaker lined up for sure. I'll remind everybody that as we go through today's program, you can leave your thoughts, comments, and questions for our guest speaker in the chat box or in the comment thread. Just type those up as we're going along. We're monitoring those. I've got them pulled up right here so that after today's presentation, we can go and have a conversation with you. So make sure you're putting stuff in the chat. If anything, just drop like a little waving hands emoji to say hi and let us know that you're here tuning in for the program, because we're so glad to have you. I'll let everybody know too that we do have live closed captions available for today's program. There's a link in the chat box on YouTube. Click that link and it can take you to the captioning page as well. Let's see, what else? Oh, I almost forgot. Happy Earth Day, everybody. Now, it's not Earth Day yet, but I won't see you all tomorrow, April 22nd, when it is Earth Day. And so this being the closest Wednesday to it, we are celebrating Earth Day with you today. Of course, April basically is Earth Month for us at the Museum of Natural Sciences, right? Like we have a giant globe on the outside of the building. How could we not celebrate Earth Day and just go ahead and make it all month? But this week in particular, we've been celebrating the Triangle SciTech Expo. We've had great programs that started on Monday that are available here on the museum's YouTube channel. And we have more programs this afternoon running all the way through Saturday, and a lot of great programs to check out, specifically tomorrow on sustainability to celebrate Earth Day. So make sure that you check out naturalsciences.org, click the link for the Triangle SciTech Expo, and check out all the programs that are coming up. They're all free. Most of them are happening right here on the museum's YouTube channel. You can also register for programs to get reminder emails. Make sure that you check that out. Okay, I think that was all of the announcements that I had for today. I had a long list of them. Let me introduce today's guest speaker. Dr. George Elvin is an associate professor of architecture in the College of Design at North Carolina State University, and he is studying nature in order to improve design. Dr. Elvin, welcome to the show.
Thank you, Chris. Thanks for having me. And as Chris said, happy Earth Day Eve to everyone. And me share some slides with you about nature's lessons for adapting to extremes.
Looks great.
So, you know that we live in interesting times, for sure. Interesting things happening around the world, some of it rather challenging with respect to nature and climate crisis. This view of a new activity for people is being spectators at natural disasters, taking selfies, that kind of thing. So this is rather interesting times that we live in. And of course, it's not all good news. It's quite challenging in some ways. And so what I do with my research and teaching and pretty much my life is go to extreme places and take my students there and look at how nature has been adapting to extremes for a very long time. And as our environment gets more extreme, then can we take some of those lessons from how plants and animals adjust to extremes in their environment and make better buildings and other things? But my area of interest being architecture, I tend to focus on the architecture side of things. So some of the solo trips I've done, I've been to the windiest place on Earth. On the left there is Mount Washington with a world record 238 miles per hour. Fortunately, it didn't hit that while I was there, but it was still an interesting experience. On the right is the wettest place on Earth, Mount Wai'ialeale on Maui in the Hawaiian Islands, which receives an average of 55 feet of rain per year. So you start looking at how do things survive and even thrive in these environments. You see some very interesting things. I also, when I can, take my students to these places. This is Death Valley, and took my students there. Hottest place on Earth, of course, Death Valley. Mount Baker in the northern Cascades, not too far from Mount Rainier, is actually the snowiest place on Earth. One year they got 95 feet of snow, a single year. And it's a testament to climate change in this photo when I took my students there at a time when during that record snowfall year, there would have been about 60 feet of snow in this spot up on the mountains. We are there in t-shirts. So my students are learning all kinds of lessons. They are also looking at how nature adapts and applying those lessons to their building design work. So why do we do this? This chart, and rest assured this is the only chart you'll see in the next hour. I know those can be a little mind numbing, but it's important to think about, what are we adapting to? Why is adaptation or resilience, you hear that term now and more and more, important. And as I've said already, the climate is changing fast, and you can see how fast. This is global temperatures, and you see them going upward. Now, if you notice at the top on the right, the temperature there, a little over 2 degrees Fahrenheit in the last 80 years. 2 degrees Fahrenheit might not sound like a lot, but in terms of global temperatures and geological time, it's actually kind of astronomical. If we were to stretch this chart back over, millions of years, this sudden spike is actually quite dramatic and a little disconcerting. Last decade was the hottest decade since records started being kept. And last year, like most of the years preceding it, continues to be the hottest year on record. So what does this mean for us? Let me draw on the United Nations Committee on Climate Change. And you notice here, top of that bar, if we swing over to the left side there, 1.2 degrees Celsius. So that's what we've done in the last 80 years. United Nations Intergovernmental Panel on Climate Change. I won't bore you with too much government speak either, but this is a very respected body of over 100 leading scientists looking at climate change. So we're at 1.2 degrees Celsius of rise already relative to a baseline of 20th century temperatures. If we hit 1.5, that's just 0.3 degrees Celsius. Then we could see, and honestly, we are already seeing, loss of habitat, sea level rise, shrinking ice caps, increased desertification, more storms, that kind of thing. So, this is cause for concern.
Sorry, Dr. Elvin, I'm going to jump in. Can we go back? I'm going to say a couple of slides and start again. We ran into a technical problem, and so a number of folks have missed the last little bit.
Sure.
My very deep apologies.
Oh, that's fine. I guess the question is, how far back?
Let's take it from there.
Sure. Okay, and we're good to go?
We're good to go.
All right. So I take my students to extreme environments like you see here, Death Valley, the hottest place on Earth with a world record temperature of 134 degrees Fahrenheit. I've taken them to Mount Baker in the Northern Cascades near Mount Rainier, snowiest place on Earth. One year they had 95 feet of snow. And we are looking for lessons from nature that we can apply in architecture, of course, to the design of buildings, but really it applies to, our lives moving forward in the 21st century, challenged by a climate crisis and how to adapt to it, or any field really. And so you're seeing here the rapid increase in temperatures recently. Last decade being the hottest decade on record, last year being the hottest year on record. And I want to call your attention to about where we are right now with current increases over that baseline where things change from blue to red. Is the average global temperatures for the 20th century. So those numbers on each side there that you're seeing is the increase over that average. So we're at a little over 2 degrees Fahrenheit increase, or 1.2 degrees Celsius. Why is that important? Well, if you look at what the United Nations Intergovernmental Panel on Climate Change has to say about it, they're talking about what will happen if we hit 1.5 degrees Celsius, which is only 0.3 degrees Celsius higher than we are now. And if we continue, by the way, that trend on that graph last slide, we will hit this by 2030. And you can see, if you read through some of these consequences, we're actually already experiencing these. They're just talking about, well, they're using the term devastating, which is a little disconcerting. And this, of course, has, I won't use the word devastating, but very significant impacts on us, on life on Earth and our lives, our personal lives as well. But I'm not, here for the doom and gloom side of things. I'm here for the solution and the how do we thrive and how do we adapt to these changes in a way that we can have great lives on this changing planet. So I take my cue from a 20th century architect who actually taught briefly at NC State, that we're called to be architects of the future, not its victims. So, me, my students, you probably, if you're the kind of person that joins this kind of talk, are doing something about this problem. So what I do is look at nature and how plants and animals adapt to the world's existing extremes by going to the most extreme places, and then try to apply those lessons and get my students to apply those lessons to design, in my case. Because what better teacher is there really of resilience or adaptation to extremes? This is what nature does. This is what nature has always done. Living things are, first and foremost about survival, and that requires adaptation and resilience. And so you can see how one of the more famous architects believed in that as well. And what we'll be talking about today is those principles. A lot of people focus on forms in nature and drawing lessons from them. And that's great, the shape of the nautilus shell or whatever it might be. That's very valuable. But I think with respect to adapting to this rapidly changing environment of ours, you have to look at, why is the nautilus shell that shape? And that kind of thing, and look at those principles behind the forms. That's what Frank Lloyd Wright was doing. That's in some ways what the builders of the Blue Mosque in Istanbul were doing. I want to get now into some specific examples, both from nature and from architects, and we'll look at architects from all over the world in different spans of time as to how they took lessons from nature and adapted them. And so we're going to zoom in on the minarets here as an example of learning from nature. Now I'm going to compare the form of the minaret to a certain form in nature. And who knows, this was built long, long ago, so we can't know what the architects were thinking, but I think we can always make connections between what we see going on in nature and what's going on in our lives and distill lessons for adapting in our lifetimes. What you're looking at here is the kind of diagram that engineers do to study stresses in a building. So the color code goes from most stressed at the top and bottom to a middle ground there of no stress where the spectrum is green. And what you're seeing between that and the photo of the actual minaret is that scale applied to the minaret. So they were actually able to put sensors on this particular minaret and study how it moved in the wind or even, an earthquake tremor, something like that. Frankly, it's amazing that these minarets have stood so long, and I was curious about why. I started looking into it. And what's significant about the green color is that if you look at the chart on the left, green means no stress. And normally a diagram like this would be multicolored. There would be stresses concentrated. There would be reds and blues and greens. This is uniform, no stress across this whole thing. How did they do that? So I'm not going to get into the engineering details of it, but I do want to compare it to a form in nature, actually, which does the same thing, maybe even outdoes the remarkable engineering of the minaret. So the minaret is basically a hollow tube reinforced by a spiral stair. It's not unlike, in principle, the seagrass that we see on the Outer Banks of North Carolina. The dimensions of the seagrass are the dimensions of the sea bass are very different from the dimensions of the seagrass, are really astounding if you think about it in terms of the thickness of the seagrass to its length. We can't even do that in architecture. We can't build a skyscraper, proportionally with those dimensions. And if you take a slice through the seagrass, you find that it's hollow inside, even more remarkable. And so it's really quite a feat of engineering in nature. And you can see from the photo that it's all about putting those seed pods up high so that they are broadcast well, survival of the species and all that, and still being resilient to hurricane force winds. These seagrass have undoubtedly been through winds over 100 miles an hour, and they're still standing there. So in my own work, I want to mention what I do on the research side of things as well, because I'm actually building a structure right now to hopefully be as hurricane proof as the seagrass is. Hurricane Florence in 2018 did over $24 billion of property damage just in North Carolina. One storm, one state, $24 billion. That's amazing. We can obviously do better in designing our property and our buildings with respect to hurricanes. So I took a cue from the seagrass and sort of turned it on its side so that, well, first of all, the building is on stilts to get up out of the water. That's very important. But trying to make it aerodynamic, because a square, like most of our buildings are, is not a great shape to resist winds, or to cope with winds. It resists winds too well, you might say, because what we're doing is putting up vertical surfaces of our building walls, and the wind runs smack into them, and you get all this resistance. I'm looking for something more aerodynamic, like you see here, by taking a cue from the seagrass. Built a structural prototype last summer. This is it under construction, not the finished thing. And I want to get a little bit into another detail about that with another example of resilience from nature, which is the coastal live oaks. So this is from Myrtle Beach State Park, South Carolina. And you can see how the coastal live oaks there in the background make a pretty impenetrable shield against the hurricane force winds. I went in under that canopy, and this is what you see. You see the branches entwining to resist the hurricane forces. So the live oaks on the coast are working together to resist the hurricane. And I learned in further study that the roots underneath are doing the same thing. So they're resisting soil erosion from high winds and storm surges, and also literally banding together to make the whole system stronger. Quite remarkable. So I picked up on that too with the framing beyond what you just saw in the photograph. That would be infilled with this sort of lattice structure more akin to the structure of the live oaks than what we would see in a conventional building. There you see a mock-up of it. And this summer, we'll be building an improved version of that out actually on the coast and testing it, outfitting it with sensors, seeing how it performs in a hurricane, and see if it really does prove to be hurricane proof. So that's some of my work. I want to kind of organize our thinking a little bit about nature and how nature adapts, and share with you some principles I have found just from all this study, you know, firsthand going to extreme environments. And I've discerned so far these 5 principles, I guess maybe as a way of structuring my thinking about what's going on in nature. How is it that nature and plants and animals are so adaptive and so resilient in the face of these extremes? So I want to go through each of these and share some more examples from nature and from architects of all kinds who are learning from nature to make more resilient buildings. So let's start with regeneration. Well, nature is just a big regeneration machine, really. That's what nature is all about. So what better place to look for examples of regeneration than nature? That is what life in all forms is all about. Survival, and not just survival of one generation, but multiple generations. In architecture, we have buildings that are doing the same. This is the Candida building on the campus of Georgia Tech University, brand new building. And it is quite remarkable, really. It has 917 solar panels that produce about 500,000 kilowatt hours of energy per year. So it actually produces more energy than it uses, because it's also extremely energy efficient in terms of its insulation and other things. And so this building is actually producing more energy, and it's clean energy, than it uses. So it doesn't need to be connected to the grid at all, except to feed clean energy into the grid. And this is, I would hope, where things are going with architecture. A vernacular example, this is from the Madon people in Iraq. Quite a remarkable challenge, really, for people living in this environment. It's a wetland, as you can see. You have basically one material to work with, and boy, do they work with it remarkably to make some very resilient, renewable structures. So their building materials are regenerative, and you know that they're making other things from this as well, this extremely regenerative and even fast-growing material. Resilience, most critical, adapting to changes of all kinds. Things are changing more quickly all the time for us, as we know, and the changes in many cases are more extreme than they were. looking to nature for this one with forest fires, we find that certain pine cones actually explode in a forest fire in order to distribute their seeds. So here's a plant actually using the forest fire to perpetuate the species. On Hawaii, see if I can get this pronunciation right, the Ohia alehua plant that you see here near a venting volcano. Ecologists have found that when those vents are extreme and that steam blasting out of there, and obviously plants can't very well survive that, that they do survive while other plants around them die. What they figured out is that, plants breathe, they breathe in CO2 and they breathe out oxygen. Well, they breathe through pores, just like air can transpire through our skin as well. What this plant does is close those pores when a volcano goes off. Of course, even this plant is no match for lava flowing around it, but the steam is much more prevalent than the lava flows that we see on TV. And so it is really built to survive these. From architecture, the Halley Research Station in Antarctica is built to move, and it's a good thing too, because as ice shelves calf off of Antarctica due to climate change, they've had to move it more and more frequently. They had to move it this spring when an ice shelf the size of New York City broke off of Antarctica. And then we have the Ganvi Lake Village in Africa, and people living on the water. And so in terms of regeneration, these people can adapt to changes in water flow, drought, flood, you name it, very creatively. It's the largest freshwater town in the world. Let's talk about efficiency and doing the most with the least. The blue whale feeds on krill, which in itself is amazing that the largest animal on Earth would feed on some of the smallest. And it does this by diving down. You see those videos of the blue whale breaching. Sometimes that's to gain height, to actually dive straight down, and those big filter teeth that they have, and they just plow through these schools of krill and take in incredible amounts of krill and therefore calories and energy. Well, some ecologists thought that must, to move the mass of a whale at that speed and over that distance must take a fantastic amount of energy. So they actually compared the amount of energy in the krill dive of the blue whale to the amount of calories gained from the krill dive by eating krill. What they found was that there was a 90 times gain in energy. In other words, the energy that the blue whale gains from eating the krill on its dive is 90 times the energy used to make the dive. That's amazing. And so we could learn, I think, a lot. Humans aren't always as good at that. If you look at meat production, for example, it takes 20 times as much energy to make a cheeseburger as we get from calories in it. So we can learn more, I think, in that area as well. Contemporary architecture, the Shanghai Tower is over 2,000 feet tall. It's the tallest building in China. That spiral form reduces the wind loads on the building, which are obviously very critical. You don't want the wind having a big impact on your building. They reduced the loads by 25%, actually. And on top of that, they were actually able to build this with 25% less steel. So clever engineering, maybe a little bit of the seagrass lesson in this one. In Algeria, the housing there in certain areas, and this is right on the Sahara. You see the oasis in the foreground, and you see the Sahara in the background behind the tower on the left. And so these people making these very thick walled structures, once again, out of about the only material available. They're making adobe out of the sand and the mud that surrounds them. Very thick walls, very few openings to be efficient and basically keep the sun out. So they're not, filling these up with a bunch of mechanically powered air conditioning. It's natural cooling. Let's talk about diversity, another aspect of nature, and how that diversity, if one aspect of your needs fail you, or your resources, can you rely on others so that you can still adapt and still be resilient? Omnivores, for example, eating plants and insects and animals and everything, so that they have a wide range. If somehow one area of their diet dries up for some reason, they can rely on others. This is the University of British Columbia Center for Integrated Research on Sustainability, and it uses a diversity of materials. The view that we're seeing here of the ground floor is mostly glass, but the basement and the back two sides of this are concrete. So it has a concrete base, nice sturdy base foundation for the building, and then a timber frame up from there, and then a lot of glass. And so you have this synergy of materials, each serving a certain function and working well together, also in this case to really optimize energy savings also. From vernacular architecture, a Chinese pagoda. Want to reveal some rather interesting things about it in terms of the diversity of its structure. And I had always wondered as an architect, and assumed it was just aesthetic, this sort of piling on of structural members. Why are we looking at like 8 structural beams here at the corner when 1 or 2 would suffice? And it turns out the answer is very interesting. Once again, in this case, some engineers put sensors all over this building during its remodeling. And so here is that corner joint kind of unstacked. And why would you go to all this trouble? Well, in an earthquake, the energy of an earthquake can be dissipated by moving the building, because a pagoda weighs a heck of a lot, and it takes energy to move it, to make it sway side to side. Of course, that's very bad news when that goes too far and a building collapses. But what if you could make the building move intentionally somewhat? You could actually dissipate some of the earthquake's energy, and it could actually be safer than if you tried to make the building, just really solid steel frame or something like that. So it appears that's exactly what they did. And they took it to one extreme. The reason I'm showing you these photos is they actually disassembled this whole pagoda and put it back together. So they learned a lot. And one thing that really shocked everybody when they did is, if you put these 3 diagrams together, those timber poles that come down that support that very high pagoda, that pagoda is like 10 stories high or something, is not set in the ground and has survived all these years. And that's just amazing. But again, I believe they did that intentionally so that the building could move a bit. So the joints are built to move, the building as a whole is built to move. And then, of course, if you hit if you have the misfortune of an extremely heavy earthquake, then all bets are off no matter what kind of building you have. But they guessed right, and this pagoda has survived, and it's just remarkable. It's, right up there with the seagrass in terms of engineering, that they could make a structure that tall and skinny, that heavy, that isn't even set in the ground. That's quite remarkable. Last principle, I believe, is the interdependence of things, how things rely on each other for survival. The Amazon rainforest, for example, is home to an estimated 50 million species. So it's the granddaddy of interdependence and diversity and that kind of thing. The ants alone, they say there can be more species of ants on one bush in the Amazon rainforest than in all the British Isles. A building example of that from a clean energy perspective is the Nova Scotia Community College Center for the Built Environment. It has solar collecting walls. It has geothermal pipes. The pipes in the foreground are actually running cold water through the building. And then the warm water from the building, after the cool water has absorbed heat from the building, go back into the ground where they're cooled again. So it's extremely low energy, extremely efficient, clean. It's a closed loop. It's just running water. And you just have a little bit of energy, probably powered by those solar walls, to run some pumps to circulate the water. It has a green roof. It even has wind turbines here. So a variety of clean energy sources, so that if you get a cloudy day that cuts into your solar, or a still day that cuts into your winds, then you still have clean energy backup. The Khasi people in northeastern India have built living bridges. So what could be more resilient or greener than living architecture? And so they have this interdependent relationship where their livelihoods, their transport, probably their commerce, even their education, as these guys appear to be going off to school, depend on the well-being of that living tree. And they manage the roots and they care for the tree so that they can have this living bridge there. So that's some principles from nature that I hope you can take lessons from, both from nature and from designers who have worked in harmony with nature for being resilient in the face of adversity. Yes, we have challenges ahead with our climate crisis, but if we look closely at nature, I think we can learn lessons that can really do us a lot of good in terms of living more resiliently, and that just guarantees a better future for all of us. So as I mentioned, while the climate crisis may be the biggest challenge humanity has faced, it's a great opportunity for adaptation and resilience. And it's a great opportunity for design, anyone in design too. So I will close with this quote from, again, architect who taught at NC State briefly, Buckminster Fuller, that the best way to predict the future is to design it. So whatever may come in the future, it's really up to us to, strange as it may sound, work in harmony with it. I don't know that resisting nature is a winning formula. I think if we can adapt to it and work harmoniously with it, then we'll all be better off. And with that, as soon as I can get to my very last slide, I will ask for any questions you might have.
All right. Thank you so much, Dr. Elvin. Excellent presentation.
Thanks.
So everybody, I'll remind you, drop your thoughts, questions, comments over in the chat box on YouTube. I've got that all pulled up and I'll be turning there in just a moment in order to start the conversation and bring all of our viewers into the show today. But Dr. Elvin, I'm curious why some societies, and I'm thinking like Western societies, seem to have turned away from using nature-based principles in design, like building square houses in very windy places, or rigging up electronic air conditioners in places where it gets hot instead of just thick walls like the housing in, was it Algeria? I think you
Yeah,
mentioned, on
yeah.
the edge of the Sahara. So why do we turn away from those principles if they work so well?
Yeah, yeah. Well, that's a very good question. And two answers come to mind. One is because we can, because in the last 100 years or so, we have had the luxury of fossil fuels to burn, and that just put the whole system into kind of a tailspin in a positive way at first. Woohoo. I mean, they say that there is more energy in a liter of crude oil than in 40 years of one person's hand labor. So you get the seductive aspect of fossil fuels. It was irresistible. And at first we didn't see the downside of their use. Now, of course, we're seeing that with the greenhouse gas emissions from the burning of fossil fuels, playing such a big role in the climate crisis. But we still have that mindset of, wow, can we just burn more oil or something, to get ourselves out of this mess? No, we're actually going to make it worse if we do that. And the other big one is education and detachment from nature, that we don't see those lessons anymore. We spend 90% of our time indoors, et cetera, and we just miss those lessons. So they aren't part of our lives the way that they can be, say in an indigenous society or something like that. But they're still out there, and we can still get out there. And a lot of us have, with COVID, and that, I guess, was one upside, was people got outside more. If we can keep doing that, keep noticing what's going on, both how the environment is changing, because I think that's a big issue education wise with climate change too, is that when we're sitting in our air conditioned homes, like I am right now, I'm not preaching, but we don't notice, that, like the chart that I started off with, that things are getting hotter or the storms are getting bigger, because we are insulated from it. And so we can understand the problem better if we get out in nature more, but we can also understand the solutions better by seeing how nature adapts.
Excellent stuff. So Lisa's writing, or asking if you can talk about storm debris from a traditional home, in addition to issues with petroleum and wastewater spills and other pollution attributed to storm damage to buildings.
Mm-hmm. Yeah. Yeah. I mean, it is a big issue when there's flooding, like with a storm surge. You have a lot of surface oil from cars, for example. Uh, we have, the confined animal feed operations in North Carolina, where the waste, in a flood gets into, the entire ecosystem, all kinds of concerns. And then, of course, you got things like ocean plastic pollution. And yeah, so it's very significant. What they find in what they call forensic studies of buildings that have been damaged or destroyed by hurricanes, it's not the structural members that fail, it's the fasteners. And so what that means is you've got actually these large building components. Buildings aren't shredded in a hurricane, but they are sort of dismembered, you might say. Like they are almost returned to the construction materials, the individual construction materials that they started in. What that means is that you have 2x4s flying around and punching through, mobile homes with, thin walls and pretty bad situations. You do have small degree. You have toxic materials from buildings. Buildings, we still use a lot of wood and some benign materials. There are, unfortunately, a lot of toxic materials in buildings too. Some of the insulations and different things that are getting into the ecosystem. So yeah, the bigger and more frequent storms and flooding we see, then the more of that stuff is going to be getting into the entire ecosystem and not be sequestered in buildings the way it is right now.
Excellent. All right. The next one is from John. Is there a spiral structure inside the seagrass that mimics the spiral staircase in the minaret?
Yeah. yeah, that would be cool. I don't know the details really, except from my own on-site experimentation with slicing up a piece of seagrass. What I have found is that it's like bamboo, which of course is also hollow, but then every once in a while it has a solid disc. It has sort of joints almost. And that the seagrass does that too. Where you see leaves sprouting off from the seagrass, there's a continuous joint across. From an engineering point of view, my guess is that the hollow structure greatly reduces the weight to shape or weight to mass ratio. If the seagrass was solid, it would weigh so much that it would fall over. And by making a hollow tube, then the seagrass can grow taller and still be lightweight.
Although, that makes me think, when I see plants, maybe seagrass too, blowing in strong winds, sometimes they can bend to the ground. They don't break, they bounce back, the plant's fine. But I feel like a built structure that did that wouldn't quite serve the same purposes that we have too. What do you find are the limits of us, using bricks and mortar or dead trees?
Yeah, yeah. Well, there's two different ways to interpret the limits. In my own work, I'm actually starting with what would a hurricane-proof house look like, and sort of work backward toward the market, you might say, from there. So, I recognize that a tubular structure might not be everybody's cup of tea, aesthetically speaking, but it's a lot more hurricane resistant than a box with a pyramidal roof on it. But as a practical matter, those limits are set very strictly actually by building codes. And it's amazing how little deflection they allow. I mean, in a way, it's understandable because it's very disconcerting. Like if you have been up in skyscraper, like the Willis Tower in Chicago, for example, if you're up in the top of that, you can feel that moving, and it's a little uncomfortable. It's not going anywhere, but it's still a little disconcerting. And then, of course, for residences, we have much stricter deflection limitations, as they say. So, it's understandable that the building code limits that, but I would agree with what you're saying, and certainly with the research work that I'm doing, I'm allowing for movement in certain ways that I didn't, get into, so that you can, like I was saying, diffuse some of that wind energy. Same would be true with an earthquake, just by moving the building a little bit, sort of a bend, don't break strategy, like you're saying.
Thank you. All right. A different Chris is asking, are there other design ideas that you have for Carolinians facing more prevalent impacts from nature turned on end?
Yeah. Well, one of the biggest factors is where you live. And of course, that's a very complicated matter with respect to the Outer Banks and things. And, multiple generations living there, or even people who just moved there. Nobody wants to hear the word evacuation or relocation or anything, but where you live is seriously a factor. We can't control hurricanes long term. We need to do what we can now to reduce carbon emissions, so that in the long run we don't have this exponential increase in temperatures and climate change and climate hazards, as we say. But there's not a lot in the short run we can do about, like, sea level rise, for example. There are things that one can do to an existing home that maybe weren't done in an older home. Building codes, of course, have gotten stricter in the face of more severe hurricanes and more frequent hurricanes, that kind of thing. And so those are enforced on new buildings, but it's rare that municipalities will will force anybody to upgrade their building. I did live in Berkeley, California, where all of California made you tie your building's wood frame to the concrete foundation, whether you liked it or not. It's like, you're going to do this, and
Oh, wow.
it could come to that. Yeah. For example, you're not going to see new homes built on the Outer Banks that aren't up on stilts. That's for sure. Nobody's going to let that happen. And as you may have noticed, we are seeing buildings being put on stilts. That's no small task, but it is being done. If you love your home and you want to stay put, then we're seeing that done. Shutters would be an important one. If you have windows that aren't up to hurricane resistant specifications, then there are shutters that you can add to an existing conventional window so that it doesn't get smashed in high winds. Another one worth mentioning is a metal roof. Actually, that's a big one because these asphalt shingles get shredded pretty quickly in high winds, and the metal roofs are much more resistant to wind.
Lots to think about on that front. Goodness. Well, Katie's got a good follow-up, actually, or it works out to be a nice follow-up question. How open are home building companies to adapting the new homes to some of these building principles?
Well, that gets us into the market drive. I mean, It is remarkable to me that home sales, both the average price per home and the volume of sales on the Outer Banks, are at record highs. And with sea level and hurricanes, that surprises me. But, it's all about the market, and builders are going to, play to that market. And if there's no demand beyond what the code requires, if people aren't asking for additional safety features, then, most of them aren't going to provide it. If from the buyer's perspective, something is being added to the cost and it's not something that they really want. Now, to me, that's wishful thinking on a buyer's part, to think they can get away with a house that isn't built to very high standards with respect to sea level change and hurricanes. But the market is what it is, and demand is going to drive the design of the supply.
Could communities like Hampton Roads, Virginia, who are dealing with sunny day flooding, gain any insight from places like Venice, Italy?
Yes. By the way, what Venice is doing now, I was there about a year ago, and they had just made the decision to leave the temporary scaffolding that they had put down on the sidewalks along the canals in place permanently, because they were so sick of putting it up and taking it down after a flood, and then a week or a few weeks later having to put it back up for the next flood because the sea level rise is so extreme there. So now they've just left it in place. So we're seeing this kind of ad hoc response. And I don't think, let's see, coastal communities don't have the option that Venice has. They already have in place pretty extreme breakwaters and seawalls and things to try to keep sea level rise out. Now that is and New York is trying to do the same, actually, because they're not going to relocate Manhattan, and they're not going to relocate Venice. So, what are they going to do? Boy, that's a high dollar, very difficult task. And I've heard that, Avon, for example, the town of Avon on the Outer Banks is doing beach refurbishment again with, I believe it's an $18 million price tag, after they just did it 3 years ago. They're having to do it again. The sea level rise and erosion are happening so quickly, and governments aren't coming to the rescue anymore. Federal government can't bail out every town on the east and west coast as sea levels rise. So the residents are on the hook, and their property taxes are going up by 50% and more. And so it's really kind of reaching crisis level there. In terms of, I mean, to answer the question more specifically, I just actually finished up a seminar with my students looking at that exact problem of what can coastal communities do, with the means at their disposal. And it's tough on the ocean side. There are some things they can do on the sound in the case of the Outer Banks or the Inner Banks in North Carolina, for example, with living seawalls and living breakwaters made out of oyster shells and different things. But on the seaside, it's the ocean, and you can't cordon off your section of the beachfront. You can do your section of the beach restoration, but if it gets washed away 3 years later, that's not a winning formula either. So it's a tough challenge right now, to say the least.
Yeah, it doesn't sound like an easy thing to try to tackle. But at the same time, right? These are going to be, if we're talking about coastal communities, we're talking about a global issue, which means that we've got to develop the strategies for dealing with sea level rise, as an example. At the same time, we have to implement all of the solutions to tackling climate change, and all of that is just so interconnected in creating that what resilient future.
Yeah. Well, and I guess that
and I guess accepting some not risk
mm-hmm.
and not losses, but like yeah, maybe a lot of communities on the coast won't be able to continue.
Mm-hmm. Yeah, I mean, adaptation by definition means change. We are having to change our behaviors, not just our architecture or our sea fronts or whatever, but our behaviors too. So that's a big one. So yeah, you've got to mitigate the causes of climate change with respect to the fossil fuels and the rising temperatures and greenhouse gas emissions. And then you've got to mitigate the effects of climate change through this resilient design. But I guess we've come full circle now that I will point out that this is what nature does, so what better teacher? Nature is all about regenerating through resilience.
That's an excellent statement to go out on. Dr. Elvin, thanks so much.
Thank you.
Everybody can, wherever you're at, big round of applause, wherever you happen to be taking in today's presentation, clap out loud, let everybody around you know you enjoyed it, or just drop a note in the chat. Thanks everybody for tuning in to this presentation. It will remain archived here on the museum's YouTube channel. So for those folks who maybe missed a little bit at the beginning, as soon as we're done here, wait a couple of minutes, you can go back and catch everything that you missed, if that happens to be the case. Thanks for being flexible with us, everybody, including our guest speaker for being flexible. We, of course, will be back here next Wednesday at noon here at the museum's YouTube channel. So stay connected with the museum on social media. That's Facebook, Twitter, Instagram, and YouTube. And of course, you can get updates on programming by visiting naturalsciences.org. And if you're specifically interested in staying tuned in to this lecture series, the Lunchtime Discovery Series, make sure that you visit eenorthcarolina.org and sign up for the email list that they send out. They send you a reminder every week of who's coming up for the next program with what will usually be the correct link in the email. That was my fault. And then you can also follow the Office of Environmental Education on Twitter. They're at North Carolina EE. Thanks so much to the folks in that office. Thanks to the people here at the Museum of Natural Sciences that made the program happen. And of course, once again, to our guest speakers. We'll see you next time, everybody. Take care, stay safe, and keep your community safe. Bye, everybody.